All right, so like I said on Wednesday, there were just a couple more things that I wanted to go over from chapter 10. And so I'm making 2 short videos to cover that material. Making them short so you don't get too bored and hopefully you watch the whole thing. So basically, where we ended last time is we learned about the parallel axis theorem. And I think I mentioned that one of the uses of the parallel axis theorem would be to find the moment of inertia of an area which is actually made up of composite parts. So, for example, we have this picture right here, and if we wanted to find the moment of inertia of this area about either the x or the y-axis, we could think of the object of being made up of 3 separate objects. So there would have been sort of the outside rectangle, which we would imagine would be solid, then the triangle, and then the interior rectangle, which would be a hole. And so we're going to see that we're going to use the hole very similarly to how we used it for finding the centroid of a composite object. So for example, if we wanted to find the moment of inertia of this shape or this area about the x-axis, it would be the moment of inertia of the area of the first rectangle, assuming that it's solid and it doesn't have the hole in it, plus the moment of inertia of the triangle, and then we would subtract the moment of inertia of the smaller rectangle, which constitutes the hole. So now we're going to talk about, in a little bit more detail, how we find these individual moments of inertia. So basically what we know is we have a table, and we're going to look at it shortly, that gives the moment of inertia of simple areas when their axes go through the centroids of the objects. For instance, what is the moment of inertia of a rectangle when the x and y axis pass through the centroid of the rectangle? Now, what happens is, for a lot of situations, we're not going to want to have the moment of inertia for an axis, about an axis that goes through the centroid. So what we have to do is we have to adjust all those values using the parallel axis theorem. So let's take a look at that. Okay, so here's are the shapes that I was talking to you about, or the table. And so for instance, for this moment of inertia for the rectangular area, notice that the x and the y-axis pass through the centroid of the rectangle. So these values are really only valid if that's where our x and y axes are. If they are displaced at all, for instance, maybe if they're at the lower, maybe if the origin of our coordinate system is at the lower left-hand corner of the rectangle, we would have to use the parallel axis theorem and use these moments of inertia and then add a corrective term that would account for the movement of the axes. So just to remind you so here is what we're talking about. Just starting from the beginning of our process, we're going to imagine our shape is constructed of either a sum or difference of really simple shapes. So for instance, this shape right here, which is a rectangle with a circular hole in it, can be viewed as a rectangle minus the hole. So we would know, for instance, if we want to find the moment of inertia of about the x-axis, notice that this is the distance from the centroid to the x-axis. So if this is object number 1, the moment of inertia of object number 1 would be its moment of inertia when it's through the centroid, so I'll just call that primed, plus dy squared times area, where dy would be the vertical distance that the x-axis has been moved from passing through the centroid to where it actually is, and then the area would be the area of the object. And we would do the similar thing to find the moment of inertia of object 2. Of course, in that case, we would look up what was the moment of inertia of a circle, and then in this case, our dy is actually the same. And I'm going to make these to indicate that those are the areas of the objects, respectively. And so here is the equation, but this doesn't use subscripts, so it gets a little confusing. This is really what I just wrote. That the moment of inertia about the regular axis is the moment of inertia about the centroid, plus a corrective term, which is the distance that we've moved the axis, times that distance squared times the area. Once we're done with that, how we would find the overall moment of inertia, the moment of inertia total would be equal to the moment of inertia of object 1 minus the moment of inertia of object 2. So let's look at an example and do some calculations. So here we have an object, and it is a, we want to think about how we could make this really simple. So what I'm going to do is I'm going to think about the fact that we started with a rectangle. I'm going to outline that in blue. And so the moment of inertia of the rectangle. And then we're going to remove from it the circle, which I'm outlining in green. And then also we're removing from it, the triangle. And so that's how we would find the moment of inertia overall of this shape, is we would have to look at the pieces that we bring together to make it. So it's a composite area, and we're going to have to find the moment of inertia for each of those pieces. We're also going to have to use the parallel axis theorem, because if we find it about the x-axis does not pass through the centroid of any of these objects. So we're going to have to use that to find the correct value for the moment of inertia. So in this picture, what I did is I made sure that we had these tables right next to us so that we would be able to use them. So the first thing I'm going to do is find the rectangle. So the moment of inertia, the general expression for the moment of inertia about the centroid is going to be 1/12 the base times the height cubed. And so then the overall moment of inertia is going to be that moment of inertia. So that's when the axis goes through its centroid. And then we're going to have to add the term talking about how far the axis has been displaced from the centroid, and then multiply that by the area of the rectangle. All right, so now we're ready to find it. So the moment of inertia of the rectangle is 1/12. Now the base of our rectangle is 6 inches. Its height is 10. And now halfway up the rectangle, where the centroid would be 5 inches. So that's my dy. And so I want to square that and then times the area of the rectangle, which is going to be 6 times 10. So that is how we're going to find the moment of inertia of the rectangle. That, if I put in all my values, well, I've already put in all my values. If I do the calculation, that ends up to be 2,000, and the units of that is going to be inches to the 4th. All right. So now we're going to do the circle. And the moment of inertia of the circle when the axis goes through the centroid is 1/4 pi r to the 4th. The value that we're going to use is that centroid value plus dy squared times the area of the circle. So we're going to use 1/4 pi times the radius of the circle, which is 2. raise that to the 4th power. Now how far did the centroid of the circle move? That ends up to be 4 inches, so that's my dy. And then I'm going to take it times the area of the circle, which is pi r squared, which is pi times 2 squared. And altogether, that gives me a moment of inertia of 68 pi for the circle. And finally, I'm going to do the triangle. The moment of inertia of the triangle when the axis goes through the centroid is 1 over 36, the base times the height cubed. We're going to use that moment of inertia when it goes through the centroid and add the dy squared times the area of the triangle. So it's 1 over 36 times the base of our triangle is 3 and its height is 6. And then remember that the centroid here is going to be 2 inches from the top, and so we have to kind of figure out, so well, that means that the measuring from the x-axis is going to be 8 inches, and then the area is 1/2 the base times the height. Altogether, that moment of inertia is going to be 594 inches to the 4th. Inches to the 4th. I forgot to put my units up there. Okay, so those are all the moments of inertia of the individual pieces that I have to add together properly to find the overall moment of inertia. So the moment of inertia of this object is the moment of inertia of the rectangle minus the moment of inertia of the circle minus the moment of inertia of the triangle. So it's equal to 2,000 inches to the 4th minus 68 pi inches to the 4th minus 594 inches to the 4th, which altogether gives me 1,192 inches to the 4th. I forgot to do the calculation, but if we did the radius of gyration times area would be equal to I. So we would take the radius of gyration would be the square root of this total moment of inertia, and then we would subtract from it divide by it the total area, which would be 6 times 10 minus 4 pi minus 1/2 3 times 6. And so I forgot to do that calculation, which is why I don't have any of the numbers, but that's how we would find the radius of gyration. Remember, that would be sort of like, what would be the distance that we could place the entire area away from the x-axis so that it would have the moment of inertia that we've measured. All right, so that's the example how we use that moment of inertia and the parallel axis theorem to find the moment of inertia of a composite area.